Great. Welcome everybody to our first speaker series of 2021. We're so thrilled to welcome you and to welcome our speaker today, Professor George Baker, our very own faculty advisor. Professor Baker is very accomplished and well versed in the field of clean energy. He is a lecturer at the Harvard University Center for Environment, Harvard Business School, and is co-founder of VCharge, a subsidiary of OVO Energy UK, and also principal at GridWorks Consulting. He has a PhD in business economics from Harvard University and is also the developer of a 4.5 megawatt project, Fox Islands Wind Power, the largest community-owned wind power project on the East Coast. So today we'll be hearing him speak on the integration of renewable energy to the grid, hurdles to integrating renewable energy, as well as heat pumps. So without further ado, take it away, Professor Baker.
Thank you, Lisa, and welcome everybody to this semester of talks. As Lisa said, my academic career and my academic and other career has been a bit unusual. I joined the Harvard Business School in 1986 and taught there for 20-something years. My training is an economist. I'm an incentives economist. I compensation and incentive systems for managers of profit and nonprofit organizations, compensation systems, et cetera. And then by a bit of an accident, got involved in a renewable energy project on an island in Maine that involved trying to figure out how to finance. The story is there's a great wind resource in Maine. And lots of developers had gone to these people on the island and said, well, we want to develop wind on your island, so we're going to we'll build the project and we will own the thing and we will sell you the power. And these crusty old Maine folks said, not if you're from away, you won't, right? So that's their language for what it means to not be from the island. Nobody from away was going to own their wind project on their island. So they wanted to have it be community owned, but the financing of that just looked impossible. So I was on sabbatical and I spent my sabbatical year trying to figure out if it was possible to finance this thing. And I discovered a bunch of things. And at the end of my sabbatical year, I said, shoot, somebody ought to do this. This might actually be possible. And so I ended up doing it. So I ended up being essentially the developer of this renewable energy project on this island in Maine. And in the process, got very interested in questions of grid integration and how you would actually get a lot of renewables on the grid. It turns out that there's all kinds of problems with getting to a highly decarbonized energy system. But one of the big ones is electrification and grid integration. And that's what I'm going to talk about for probably the next 15 or 20 minutes. The problems, as I see them, associated with electrification and high levels of renewables penetration on the electric grid. And I'll spend the last 5 or 10 minutes talking about the thing that I'm the most interested in, and that's, I think, the biggest opportunity, in some sense, the lowest hanging fruit in this area, which is what we call transactive energy management, taking existing and new loads on the grid and turning them into part of the solution instead of part of the problem. Okay, so that's what I'm going to do. Let's see, a couple of things. I have about 30 to 40 minutes worth of stuff to say. I'm perfectly happy to talk through that and then have questions and a discussion at the end, but I'm equally happy to have you stop and ask questions as you go along. I'm not great at keeping my eye out on the little hands. So if somebody sees a hand go up, just shout out and tell me, George, there's a hand up, and I'll stop and I'll take the question. Okay, so please feel free to interrupt me with questions, with comments, any of that stuff. I in some sense I prefer that to having this talk and then this sort of awkward question and answer period at the end. So I'm very happy to take questions as you go along. If there's anything you don't understand, think is wrong, think is interesting, whatever. Okay. So I'm going to have to move. I want to see people, but I want to also be able to see my slides. So I'm going to have a little bit of trouble. So I'm going to have particular trouble keeping an eye on everybody, but I'll do that I can. Okay, so what will it take to decarbonize the energy system? Well, you have to realize exception of biofuels and a little geothermal electricity. So when we talk about getting to a sustainable energy ecosystem, we have to electrify. And we have to electrify just about everything. So we're going to ask the question, handle it. Wait, I just did saying my internet was not great. Did I go any with problems anybody's noticing? Hear me?
Yes, we can hear you.
Yes, you can hear me okay? Okay, as I say, I got a message on my screen saying my internet connection wasn't good, but it sounds like it's going okay. It's going okay? Okay. Okay, so the question that we're going to look at is, can the grid handle serious electrification of the energy system? So let's look at what this looks like. Let's see what the energy system looks like with respect to the grid. So the amount of energy that gets moved in the US electric grid on average is roughly 360 gigawatt hours per hour. That's the average number. Okay, you could think of that as just being 360 gigawatts is the average power of the grid. Okay, this is everything. This is what we use, everything that we use electricity for. It's a lot of household appliances, and then there's a bunch of commercial load. There's a bunch of air conditioning. About 10% of it is actually just illumination. And then there are large industrial and commercial loads as well. Okay? You'll notice that it's only a little over a third of the US total grid capacity. US total grid capacity is a bit of a misleading number because what does that actually mean? And I'll tell you what it means is it means the maximum amount of generation that could be on at the same time. But it never is, because the peak in New York City is different at a different time than the peak in Chicago, which is at a different time from the peak in California. So the US grid is never actually at a terawatt, which is 1,000 gigawatts. But in theory, could move that much energy on the grid at the same time. In theory. But as we're going to see, there's all kinds of problems. Okay, so currently we move about 360 gigawatt hours per hour through the grid on average. Oil and gas, we move about 560 gigawatt hours per hour of energy. This is delivered in pipelines and big oil trucks. Most of the residential and commercial use of oil and gas is for space heating. And then there's a whole bunch of industrial use for a whole bunch of other things, including petrochemicals, a whole bunch of other things that they use oil and gas for in various industrial processes. But as you can see, if we tried to move that much energy around on the grid, we would start getting into serious trouble. The grid is nowhere near going to be able to handle moving that much energy electrically, and we haven't gotten to the big one yet. The transportation sector requires about 900 gigawatt hours per hour of power to keep the cars, the trucks, the boats, the planes, the trains moving. Okay. So what you can see is electrification is a very significant challenge to the electric grid, because once we take all of those other uses of energy and convert them over to electric, the grid is going to be totally overwhelmed. Now, say, whoa, wait a minute. That's not right, because you told me that a bunch of this stuff was space heating, and in the future, we're not going to do that with resistive electric heating, which is what this represents. We're going to do this with heat pumps. And heat pumps are about 3 or 4 times as efficient at extracting usable heat from a kilowatt hour of electricity. True enough. So this number won't be that big, okay? It'll still be a big number, but it won't be that big. And then another group here say, wait. Internal combustion engines are only about 20 or 25% efficient. Electric are about 90 to 95% efficient. So that transportation number should be smaller too. So I'll go ahead and make very generous assumptions for increased efficiency of heat pumps and internal combustion and electric versus internal combustion engines. And we still get a picture that looks like this, right? And you go, oh, good, we can make it, right? Except that we can't possibly make it, because what this says is that the average load required on the grid equals the peak load that the grid could possibly produce. That would mean that the load would have to be absolutely flat and the same all the time, or we would be blowing through the capacity of the grid all the time. And we see right now, the grid is about 3 times as big as the average load, a little bit less than 3 times as big as the average load. So we need to actually start looking in a good deal more detail at what it means to say, what can the grid do? Because this is a very scary, you show this somebody who actually runs an electric grid and they'll say, this is completely possible. We have to build. So what is it? How is it that the grid works, and what's the problem? And the problem, of course, has to do with time and place specificity. And the problem with decarbonizing and going to renewables is that renewables are time and place specific as well, very time and place specific. So let me talk specifically about solar and wind to kind of highlight the problem, okay? Solar, obviously time specific and correlated across space. Solar peak generation happens the same time in California, Northern California, and all basically Nevada. You get this very highly correlated peak in generation if you have a lot of solar. That's why the California duck curve looks like it does, as I'll show you in just a minute, okay? Diurnally, it is poorly correlated with load. We'll look at these load profiles in a minute, but basically what the load profile on the grid looks like is there's a peak in the morning, which I call the coffee pot peak, and then there's a trough in the middle of the day, and then there's a peak in the evening, which I call the television peak. And that's basically what it looks like, except in hot weather. In hot weather with a bunch of air conditioning, it actually goes more like this and peaks at about 4 o'clock in the afternoon, and then starts coming down as the air conditioning peak dampens out in the evening, right? But the point is, it doesn't look like solar generation, which is basically an upside down bowl peaking at about noon or 1 o'clock in the afternoon, okay? So you've got poor daily correlation with load. In subtropical places, Southern United States, Southern Europe, it's actually a good match seasonally because solar output is significantly higher in the summer, which is when you need the power for air conditioning. So it's not bad on a seasonal basis. In southern latitudes, it's terrible in northern latitudes. People who are trying to put solar in Maine are realizing that it's just a disaster because they don't have much load in the summertime, and they have almost no solar in the wintertime. And they use much more electricity in the wintertime than in the summertime in places where you don't have air conditioning, okay? The other little known thing about solar, which is actually very important and scares grid operators a lot, is that it ramps super fast. And what I mean by that is sun goes behind a cloud, you lose 80% of your solar output in a few seconds. Okay? That trip out most thermal generators. Most thermal generators can't handle a loss of a plant that fast. Okay? And so you got to do something to keep those kinds of high-speed ramps from hitting the rest of the grid, or you're going to have difficulty with keeping the grid up and running. This is why grid operators in Ireland, in Germany, in Denmark are very worried about what happens when they let their renewable penetration get above about 30 or 40%. They just start saying, we are going to have stability problems on the grid.
Hi,
now,
Professor
of course,
Baker. Sorry to interrupt.
Please.
I just had a quick question about this change in
apologize
ramping.
for interrupting. I'm delighted to have you interrupt. Yep, go ahead.
Yeah, I'm just wondering if you could speak a bit more about the challenges posed by ramping speeds and, like you say, this instability added to the grid. Like what exactly is happening on the grid and what mechanisms are currently in place, if there are any.
About the wind. Let me explain about the wind, Lisa, and then I'll come back and talk about exactly that. I don't have a slide on it, but I'll tell you what happens, okay?
Sounds good. Without
getting too far into the physics of synchronous generation, which we won't do today, okay. So notice that geographic diversity helps. If you've got a bunch of solar farms, the cloud isn't going to come in front of the sun at all of them at the same time, right? So you'll get a slower ramp, but that's only all of those things as if they're a single generator. It can't. We have a similar problem with wind. Wind is, by the way, not particularly time specific, but it's very intermittent and also strongly seasonal. It's not quite right to say, but it's basically right to say wind is essentially, there's no windy time of day. That's not completely true, but generally speaking, the right model of wind for the average is that it's about flat across the day. It's not flat at all, but there's no particular pattern to it. There's a great counter to this though, actually, which is that So one of the very attractive things economically about the Cape Wind project, which got canceled a few years ago, it was going to be a huge offshore wind project off of Nantucket and Martha's Vineyard. Those of you who have lived, who are from or who've lived in New England for any length of time know that we have a phenomenon in New England called a sea breeze, which on hot summer afternoons, you will often get a fairly strong wind off the ocean in coastal areas. Well, Cape Wind was going to catch that sea breeze and turn it into electricity. Exactly, electricity prices were at their highest when the air conditioning peak was to be 4 or 5 o'clock in the afternoon on hot summer days. And so this actually substantially improved the economics of Cape Wind because of this meteorological phenomenon of sea breezes on hot summer afternoons. Okay, so at high latitude, it's a great match seasonally, right? In the northern parts of the United States, the wind blows a whole lot more in the wintertime, which is when they need the power. But it also tends to be quite variable on a kind of 10-minute basis. Okay, so now I want to come back and answer your question or discuss your question a little bit, Lisa. So let's see, what's a good example? We could as easily talk about an electric motor as a generator, but we'll talk about a generator. So a generator is sitting there spinning, and it's spinning at exactly 60 hertz so that you get the right, amount of, that you get the frequency that you want. Every generator on the system is completely synchronized to system frequency. In the US, that's 60 hertz. In Europe, that's 50 hertz. So they're all sitting there, and it's called synchronous generation. And they're all going along, and grid frequency is nicely at 60 hertz. If over a short period of time, and by a short period of time, I mean seconds, you eliminate a bunch of generation. Okay, so let's say a big power plant trips off, or a cloud goes in front of your solar farm and it's really big. Okay. All of a sudden, all of these big spinning wheels, which all have to be synchronously spinning, load now exceeds generation. Because generation just went away, load didn't change, load exceeds generation, and those big spinning wheels slow down ever so slightly in order to catch up with the load, the fact that they're having to deliver more load. And the way that they deliver more load is they give up some of their stored energy, some of their stored inertia. And the problem is, if this doesn't happen absolutely uniformly across the system, the weak link in the system, some generator somewhere is going to go, wait a minute, the frequency coming in is one, I'm spinning at another speed, I'm out of here. And the next generator will trip out because it can't handle the changing grid frequency that it's confronting, its own speed versus the speed of versus the sine wave that's coming in. Well, so now another generator is tripped out, and you can see how this story ends, right? And this story ends with candles and oil lamps. Right? Because the second generator goes out, system frequency drops a little bit more. So this is literally how blackouts happen. Okay, at a physical level, this is the way blackouts happen. And it happens usually because a large generator trips out. But it can also happen because a cloud went in front of the sun, right? Or the wind all of a sudden dies. Wind doesn't die that fast. Wind is much less likely to trip out thermal generators, but this 10-minute ramping is a much bigger problem because that can happen over a huge area. The wind can die down quickly, and you literally cannot fire up big thermal plants that fast. You have to have a lot of what's called spinning reserves. That means generators sitting there spinning, ready to go. They're turning at exactly the 60 hertz frequency, but they're not actually generating any power. Right? They're not generating any electricity. They're burning a little bit of fuel to keep going, and then you can give them more fuel to give them more. But that's a very expensive proposition to keep a whole lot of spinning reserves running all the time to deal with this kind of stuff. Okay, so that's basically the problem that we have with ramp rates and with very rapid changes on the generation side. By the way, it can happen on the load side too. If you get a major line to a large load going out, you can get ramps up in system frequency, which are also hard for the electric grid, for the existing thermal generators but nearly as often. Okay, so this problem with the fact that wind is coming up and down. It's highly intermittent, right? So sometimes it's there like crazy for a bunch of the time, and then it's not there for long periods of time. Makes the story from this morning's Washington Post. I read this and I just guffawed, right? So the world got a little bit greener when the lights on the Empire State Building for life this year. For the first time, the beloved skyscraper and 13 other office buildings owned by the same company were powered solely by wind. The Empire State Realty Trust will announce Wednesday a major purchase of wind power from Green Mountain Energy in Vermont, making it the nation's biggest real estate user of entirely renewable energy. So do you know what they actually did? They bought all of the output, or a fraction of the output, from Green Mountain Energy in the amount over a year that the Empire State Building and these 13 other buildings will consume in a year. But to say that they are wind powered is completely ludicrous, right? Because they are not wind powered at all. If they were wind powered, you would see their lights flickering on and off and getting way too bright and popping all the light bulbs because there would be way too much power a bunch of the time. And I mean, I can tell you, Green Mountain Energy has about a 30% capacity factor. That means that it's only operating, it's not true, it's only operating a third of the time. It's operating more than a third of the time, but its equivalent maximum output, its total output is only about a third of its theoretical maximum output, what it would output if it was generating at full power all the time. Okay, so it's going up and down all the time, and often way more than the Empire State Building needs. And a whole bunch of the time, it's generating nothing. And I guarantee you Empire State Building is not turning off its lights then. Okay, so this is just not in the slightly quantum mechanical question about whether the electrons actually can even find their way from Vermont to New York City. And the answer is, in theory, they can. There is a copper path from Vermont to New York City, but those are two separate grids. The ISO New England grid and the New York ISO are connected, but not very well connected. Those lines are frequently fully congested. So the notion somehow that the Empire State Building is powered by wind is really something, if you know anything about the electric grid, you're skeptical of this newspaper article. Okay. Yeah.
I was wondering, why do they not just use or I guess are you like, I'm saying that they use like solar to directly power things? Like it goes directly from like the solar plant to like whatever it's powering. And that's why intermittency is an issue.
You see it occasionally, but you don't see it very often, John.
So I guess like what I'm asking is, why is it a problem if they just go like directly to like a storage area to like use at another time when it's like, I guess not.
Right. Like, so sorry, do you mean a physical store the wind power and then use it later when they need it?
Yeah, exactly. Like, so like that would kind of
hold that thought, John. Okay. Hold that thought. Right? You're totally right. Right? We can solve this problem with batteries. We'll get there in 1 second. Okay. So renewable energy is very time specific. Okay. So this is a picture that some of you will recognize, will have seen before. This is called the duck curve. And what this is a picture of is, this is for about the last 8 years, they've been tracking net load on the California grid. And you guys can say, here's in 2012, here's the load profile I told you about. There's the morning peak in the mid-morning, and then the trough in the afternoon, and then the evening peak, okay? But over the last 8 years, the duck's belly, the load in the middle of the afternoon, has been dropping and dropping and dropping. And this is not because there are fewer stay-at-home parents or any other reason. This is because rooftop solar is putting so much power on the system that it appears that the load is disappearing through the middle of the day. Okay, so this shape here is the inverse of what a solar generator generates. Okay, and so the thing that worries the grid operators is this ramp in the afternoon. As the sun goes down and everybody gets home from work, you get this wicked ramping going on the grid. That worries CAISO, the California Independent Operator, the California, quite a lot. But in some ways, the more remarkable and telling fact is the one I'm about to show you. So notice they said this is what's happening in March. So I went and looked at the prices of power in California last March. This is the last week in March in 2020. And this is 7 days. And the blue line is the wholesale price of electricity in NP15, zone NP15, which is the Northern California price zone. And the orange lines are the afternoon. I think I did 11 to 3. Okay. And this is absolutely incredible. Every single day this week, the price of power went to afternoon for is 0 negative electricity prices in California in the middle of the day. This means that electricity is a drug on the market in California at 1 o'clock in the afternoon. Literally, what does a negative price mean? A negative price means if you generate electricity, you have to pay. If you consume electricity, you will get paid for consuming electricity, right? And this is extraordinary about what happens when you put too much highly correlated, highly time correlated power on an electric grid, right? And you start, and notice, it's not that power is cheap. I mean, it's real expensive. I mean, there are in these days when the power gets super expensive. So, John, guess there aren't no batteries in California. I mean, you look at this picture and you say, if I had a battery, I could make a killing. Right? I charge up my battery right here and I sell it all back here. And then I charge up my battery right here and sell it all back. And that doesn't happen. Right? And it's not because people haven't thought of it, right? Or that they're looking at wind. Right? And the orange, the hot zones are high prices. These are prices, if you look over on scale, these are prices that have like $100 a megawatt hour for electricity over here in Iowa and Minnesota and North Dakota. The cold colors are low prices. Blue is 0, purple is negative. So these are negative prices. This is around a wind farm in Nebraska. These are negative prices. 200 miles away, electricity costs over $100 a megawatt hour. What does this tell you? They're up to these people who are willing to pay $100 a megawatt hour for it. So this tells you the grid is not what you think it is. The grid is nothing like a system that can actually move power around in anything like a flexible and sensible way. Okay? As I like to say, the grid is not an interstate highway system. This is a map of the US interstate highway system. Right? It is a high capacity direct connection between every major city. We can move goods efficiently in any direction at almost any time. Not quite any time. Don't try and drive your semi through Chicago at 8 o'clock in the morning. It will be a slow trip, right? Or through New York City, okay? So there is congestion on the interstate highway system, to be sure, right? But basically, it's an incredible system for moving stuff long distances. This is what the electric grid looks like. Those are not big lines, let me tell you. Those things, so remember the average load on the grid is 360 gigawatt hours per hour, 360 gigawatt. Green lines can carry maybe 100 megawatt hours, like a third of a 10th of a 1,000th. It's not even a third, 1% is a tiny amount. Even the blue lines only carrying maybe 3 or 4. You just look at the volts and you multiply. The biggest power lines carry 1,000 amps and most carry less than half that. Okay, so that gives you some sense for the amount of power. This system cannot do anything like what the interstate highway system does. And you can't move it at all across this boundary, by the way. Those are two separate grids. You can't move power across. There's a couple of tiny little DC interconnects here. And you can't move in and out of Texas at all. Texas is a completely separate grid physically. Okay, so the notion that somehow the grid can solve these time and place specificity problems as it is currently manifested is completely out of the question. It would take a massive investment to basically solve this problem. And of course, the time specificity problem is also helped. If prices are negative in California in the middle of the day, I guarantee you they aren't negative up in Montana, right? Because they don't have any solar up in Montana. So if you could move power around, you could also solve a bunch of the time specificity problems, but you can't. Okay, so part of the reason for this, of course, is that it's really not very easy to move electricity around. So this graphic, so this right here, this is the largest electric transmission line in the world. It is a 12 gigawatt DC in China, okay? And this is what's on the vertical axis is how much energy does it move in terms of million BTUs per hour, okay? Trans-Alaska oil pipeline when it was full in terms of million BTUs per hour. This is the number of BTUs per hour that moved by the coal trains out of Wyoming every day in terms of million BTUs per hour. I mean, what we can see is, and this, by the way, is the total amount of energy on average moved by the American electric grid every day. We're on the electric grid as we ship coal out of Wyoming. It's really just crazy, okay? So we do not have anything like the capacity that we need to move electricity around and move it through time. Okay, but let's talk about moving through time. We're going to talk about John's now. So how do we solve these problems and get to a sustainable energy system? So, of course, we solve mismatches in timing, the timing of generation and the timing of load with storage. But what we fail to appreciate is that in a fossil-fueled world, storage is really cheap. It's everywhere. If you start looking around, just start looking around your world, and you will see that there is storage in oil tanks, propane tanks, gas tanks, coal piles, right? Massive amounts of energy. You don't see these very often. So this is the largest grid scale battery in the country. It's the Hornsdale battery storage system. That bank of batteries right there cost about $130 million, stores 129 megawatt hours, which is the same amount of energy as that oil truck holds. I'm not kidding. The amount of energy stored by $130 million, the same as that oil truck. You might say, wait. You can only turn that oil into electricity 30% efficiency. So actually, if you want to make it a true apples to apples comparison, make it 3 oil trucks. But still, it's completely ridiculous. This is the largest electricity storage facility in the world. This is the Bath County Pumped Storage, hydro pump storage. That's a lake at the top of a mountain. Every day, they pump water up to that lake when electricity is cheap, and they generate it by running it down through the turbines when electricity is dear. It can store about 24,000 megawatt hours of electricity. The picture at the bottom is a modest-sized coal-fired power plant in Bow, New Hampshire. It's up on the Merrimack River. The amount of energy stored at Bath County is equal to about 1% of the coal pile that you see right there at the Bow power plant. You can see the coal pile right there. It's a big coal pile, but this whole facility stores about as much energy as 1% of that coal pile. So yes, John, in theory, storage is going to work, right? But storage in a non-fossil fuel economy is a real challenge. Right? It's just going to be very, very difficult. People are talking about it. Batteries are getting lots and lots of hype. If you listen to Elon Musk, you think this problem is going to be solved in another couple of years. He is completely blowing smoke when he says it's because it's just, it may get solved this way. I don't think it's going to get solved for a very long. We have no concept of how much storage we have in our current energy system and how important it is to making the system work. Okay.
I just wanted to add a quick note that the Hornsdale battery project, oh, sorry, there's a bit of a delay.
Yeah, no, please, yeah.
The Hornsdale battery storage project is, I think Tesla won the bid to conduct that project in Australia.
Say it again.
I
Sorry,
just
it
wanted to
what?
make a note that the Hornsdale battery project was by Tesla.
Yes, that's correct. Those are Tesla batteries. Is that the one in Australia? Hornsdale?
Yes.
Okay, I wasn't sure. Okay, so it is true that cheap ubiquitous storage combined with a major expansion of the grid would solve the renewables integration challenge. It truly would. Okay? But what I'm trying to argue today is that that's a big, big challenge, incredibly costly. And what I want to spend the rest of the next 5 or 10 minutes talking about is a different way of not completely solving the problem, but drastically reducing the size of the problem that we need to solve with copper and batteries, okay, with copper and with storage. Okay? And what I want to argue is that we need to fundamentally change how grids operate and take advantage of a huge source of flexibility that already exists and will increasingly exist in many of the devices on the current and future grid. And in order to explain this, I need to explain just a tiny bit about how grids work, actually, how every grid in the world essentially works, which is that, of course, generation has to equal load every second on all time scales, seasonally, monthly, weekly, daily, hourly, secondly, sub-secondly, generation has to equal load. That's the physics of the problem. The way this works is, so this picture on the right is the load this past, I guess it looks like it was last, this is yesterday's load on the ISO New England grid, or for the last week, okay, from last year. And you can see there's the double hump, and then the nighttime trough and the double hump. And basically what grid operators do is they twiddle this knob on these power plants to make sure that generation equals load. And it's, honest to God, only slightly more sophisticated than that. I mean, you would be shocked at how much electricity in the United States is still dispatched by telephone call from the grid operator to the generator saying, turn up the power. Okay, they have some automation, but amazingly little. Okay? And so, so load is highly predictable. Here is this morning on ISO New England, and you can see here's their load forecast for the day, and there's the actual. They do an extremely good job of predicting load. By the way, you can, if you type ISO-NE.org, I can't remember, I think it's .org, you can see exactly what's going on in ISO New England. You'll see this picture, you'll see how they're doing with their, with their prediction, et cetera. So this is the way that grids currently work, is that load is treated as entirely uncontrollable and generation is adjusted to match load. And we have, and so basically what we have is rigid demand plus flexible generation gives us grid balance. We need grid balance. We need generation to equal load all the time, right? But some types of generation are not flexible. So for instance, nuclear and large thermal plants, you can't turn them down. You really can't. They are constant and inflexible. Those are called baseload plants. They're very important. They ride along. If you go back to this picture and think about, you're never going in New England, you're basically never going below 20 gigawatts. So if you got 20 gigawatts of nuke and coal running all the time, you're fine. You might have a little bit of a problem now and then. So probably we'll play it safe and only have a 15 gigawatts of baseload. And then all of the rest of this stuff on top is taken care of by what are called peaking plants. Plants that come on during some parts of the day and get turned off. Knob twiddled up, knob twiddled down, okay? But wind and solar don't work that way. They're neither constant nor flexible. You can't just call up the wind farm and say, could you give me a little bit more, please? I mean, the only thing you do, either you have a direct telephone to God to actually be able to do these kinds of things, or you operate your wind farm at less than its full output so that you can ask for more. But then you're throwing away free energy all the time, which doesn't seem to make any sense, right? So these things are not flexible and they're intermittent. This is what causes grid operators a huge nightmare. As we increase the amount of inflexible generation on the grid, We have to get that flexibility from somewhere. Okay? And so what I want to argue is that, and by the way, this is exactly what we see, right? I bet you anything that the Empire State Building is not saying, oh yeah, don't worry, we'll flex our load to match the output of Green Mountain Energy, right? They're not doing that, right? But the point is they could do some of it, and I want to talk about this. So the solution is to turn load from the problem to be solved to a large part of the solution, to take advantage of the flexibility that already exists in much of the load on the grid. And the great thing about this is that this load already exists. We don't have to pay $130 million for a battery, right? When we've got a battery in our car, when we've got a thermal battery in our hot water heater, right? They're already there. We're putting them on the grid. The question is, can we use them to solve this balancing problem, this problem of flexibility? So let's just look at this for a second. So load, with or without storage, so this is what is called transactive energy management. And transactive loads are loads with or without storage that can communicate with the grid and react to grid conditions. So let's think about, so this requires load assets that are or can be made flexible. So let's just think about what these could be. So I want to argue any appliance, any household appliance, commercial, appliance that produces heat or cold could be made flexible at very little cost. A hot water heater already has a tank. Okay, you don't, right now, the way your hot water heater works is the second the water temperature drops below a trigger, the element comes on, huge, biggest load in your house, unless you have a big central air conditioner, biggest load in your house comes on and reheats that water right away. It does not need to do that, right? It could wait, most of the time, it could wait 6 or 7 hours before reheating your water. You're not gonna need it, okay? So hot water heaters are a classic example of a thermal battery sitting there. Space heaters can be given a little bit of thermal storage and can all of a sudden deliver the heat you need when you need it without having to turn on the electricity exactly when you need it. A small amount of storage goes a long way. Air conditioners, this is already starting to happen. So I told you that the solar peak happens at 12, 1 o'clock in the afternoon. The air conditioning peak happens at 4 or 5 o'clock in the afternoon, okay? The casinos in Las Vegas have started building ice stores underneath the parking lots. They make ice in the middle of the day when electricity prices are 0 or negative, and they melt that ice for air conditioning at 4 o'clock in the afternoon. You only need about 4 hours of storage to do a pretty good job of matching the solar peak to the thermal peak, to the cooling peak from air conditioning. Okay, so that you can, if you just start thinking, and as I say, storing hot and cold is really cheap compared to storing electricity. A thermal battery is 1/100th per watt hour of storage. A thermal battery is somewhere between a 50th and a 1/100th as cheap as a chemical battery. Okay. So anything in the home or in the office building or apartment building that produces cold can be made flexible. Most other household appliances can be made flexible. So you push the button on the dryer, and the rule is, I promise you your clothes will be dry by the morning. And now all of a sudden you have enormous flexibility in when that rather large load comes on. And by the way, if you want to have a deal with your electric company that says, no, I need it now, you push a button, it costs you $2. You have to pay $2 to get it right away. To get it by tomorrow morning you're just paying for this standard low price of electricity. Okay? So you could create, we don't think about this way. I like to say that every living thing, plants and animals on the planet, with the possible exception of the bacteria that live in the thermal wells, thermal vents in the bottom of the ocean, have learned to live with intermittent energy input. Crops do it all the time. Lizards lie out on the rocks in the sun, right? They've all learned to live with intermittent energy input, except us. We expect that when we flip a switch, we're going to get that power. When we turn the key, that car is going to come on. Sorry, you guys don't know what it means to turn a key in a car, but doesn't need to be that way. We don't need to have, and I'm not talking about lifestyle changes. I'm not talking with it. Hey, it's not hard to build in that flexibility without taking away control. It's really not hard. I've done it, okay? And then of course, the big one is electric cars, right? So right now, again, and you get in the car, it's full power the minute you plug it in. Tesla allows you to, set the time that you want to do it. But the thing is not talking to the grid and saying, hey, grid, when would be a good time for me to charge, right? Which it could do. By the way, you might need to tell your electric company or your aggregator, hey, tonight I need to charge right away because I'm planning to go out to the movies and it's a 30-minute drive and I got to have a full battery before I leave. Right? You might need to do that, and they might charge you a slight premium for that. But 90% of the nights, 99% of the nights, it's just going to sit there for 10 hours, needing an hour and a half of charge. So there's a massive amount of flexibility in what you could do with that if you could do it intelligently. Okay, so lights, televisions, electric stoves, these things are not good transactive energy modes, right? You want the lights, you want the lights. You're not going to be happy if I turn off your TV for 10 minutes because there's a slight problem on the grid, right? So I'm not claiming that everything can do it, but I'm claiming that a very high fraction of the electric load on the grid could be turned transactive. Just a small side here, and a particular pet peeve of mine. There's a big craze among energy efficiency types for on-demand hot water heaters, which have a huge load, either gas or electric, heating water instantly when you need it. And they claim these things are great energy efficiency devices because you don't have that tank sitting around wasting, quote unquote, wasting energy because it leaks a little bit of thermal and a little bit of heat from it. But they're completely missing the future. If we went to on-demand hot water heaters everywhere, we might use a few less kilowatt hours, but it would be totally inflexible. Notice what you've just done. You've just said, now every time I want hot water, I have to make a huge electric load, right? Which is crazy, right? Much better to suffer a small loss in the heat battery and retain that flexibility on the electric grid going forward. Okay. So the potential, by the way, for transactive load is enormous. Residential hot water heaters, just residential, represent about 50 watts of load. So remember, 360 gigawatt hours per hour, 360 is the average load on the grid. Hot water heaters alone are almost 20% of that. By the way, that's not quite true. Only 40% of that number is currently electric. The other 60% is gas. But once fully electrified, it will be a very, very large number. And commercial matches this. So there's almost a third of the average load on the grid is represented by, be careful, hot water heaters if they were all on at the same time, which they aren't. Okay, so it's not as if they represent a third of the total energy use, but the size of the resource that you could throw at a problem is very substantial. Right? You could completely eliminate those negative electricity prices in California by just turning on all the hot water heaters in the middle of the day. That would be plenty of load to prop up those prices in the middle of the day and incidentally lower the prices in the evening because you wouldn't have that huge load on when everybody's doing their dishes after dinner. Right? So you could, this is a very large number on the scale of the US grid. Air conditioning is another 100 gigawatts on the US grid, which could be made highly flexible. Space heating is even more, although it's highly seasonal and little of it is currently electric. The electrification of space heating is a big long-term investment. One of the problems, everybody wants to do it with heat pumps. So Lisa, you asked me to talk a little bit about heat pumps. Heat pumps are great. Heat pumps use like a third to a quarter as much electricity. Let's see. We got to be careful. A kilowatt hour is not a kilowatt hour. A kilowatt hour of electricity, if run through a resistor, will produce a kilowatt hour of heat. A kilowatt hour of electricity with a heat pump can extract from the outside and pump it to the inside between 3 and 4 kilowatt hours of heat. Okay, so when it comes to space heating, heat pumps are substantially more efficient than resistive electric heat. However,
hi, Professor Baker. I'm sorry, I think we have just a couple more minutes, so I'm not sure how much more.
Yeah, I know. I'm conscious of that. Oh gosh. Even less time than I have. I'm on my last slide, Lisa. So let me say
Okay,
this last
great.
thing about heat pumps, and then that's my last slide. So, okay.
Yeah.
So the thing about heat pumps is because you can't get things very hot with heat pumps, you can't really store energy. So they turn out to be a very inflexible load. So I am very ambivalent about heat pumps. I like them because they're very efficient. I dislike them because they're very inflexible. You need them to when you need them to come on. Can't really store the heat because it's not very high. It's very low. It's barely warm enough to keep you warm. Okay, so what does it take? Very quickly, you need to be able to communicate with these distributed loads, and you need to be able to monitor their state. You need to know how full the battery is. You need to know how hot the water is. The Internet of Things is taking care of this for us. This is a massive opportunity to hook this stuff up. And then you need distributed intelligence that can look forward and plan for the needs of the consumer and the needs of the grid. Okay? This stuff is getting cheaper and cheaper and cheaper every single day. Right? This is all it takes to create a massive change in the way the grid operates and really pave the way for a much more highly integrated renewable grid. So getting to 90% is a major challenge. It will require investment in many parts of the system, renewables, generation, wires, and storage. But transactive energy management is cost effective and will greatly reduce the need for investment in these other areas. So any time, we've got a little bit of time, we're a little longer than I expected to, for questions, comments, thoughts.
Great. Thank you so much, Professor Baker. Feel free, anybody, to jump in and just unmute yourself if you have questions.
Professor, I would like to know your opinion about transforming, for example, wind power or solar power into hydrogen batteries. Is it feasible?
Absolutely. I'm going to go off on a bit of a jag, but so yes, it hasn't been done at scale. Hydrogen is a produced gas. We use a fair amount of it in chemical plants and stuff like that. It is not made the way you made it in high school, which was by taking a beaker of water and putting 2 wires in and watching the hydrogen bubble off. Most of you probably did this. You bubble off the hydrogen, you capture an little thing, you light a match, goes pop. It's all very exciting. You've just produced hydrogen and then burned it back into water. It's not done that way. The way that we make commercial hydrogen, which is CH4. We strip out the carbon as carbon dioxide, and we have hydrogen. That's great. Now we have a nice clean hydrogen fuel, except we made CO2 in order to make the hydrogen. So it is not a low carbon fuel right now because the making of it creates CO2. You can make it in a no carbon way by electrolyzing water. It hasn't been done at scale. It's currently not cost effective. And hydrogen is difficult stuff. It's hard to store. It's very hard to transport. It's the smallest molecule in the universe. It leaks. It's really hard to make a tank that will reliably hold hydrogen. It also explodes, as we know from the Hindenburg, but so does gasoline. I mean, lots of things explode. I'm not actually that worried about the exploding. I'm a lot more worried about the infrastructure that can actually store and pipe the stuff around. But there's a massive opportunity here because picture I showed of California electricity prices is true of every single high renewables grid that has ever been actually or has ever been modeled. And what it's characterized is by periodic cheap energy, periodic free energy. So every single energy intensive activity that you can think of, what you will get rich if you think about is how to do it in a low capital cost way so that we can run that plant 30% of the time and still have it be cost effective, right? We need to be thinking about, my favorite example is water desalination, right? Water desalination is a highly energy intensive activity, okay? Therefore, all of the engineers are going around trying to figure out what they can do to get the energy content, to get the energy requirements, the energy intensity out of water desal. And in the process, they make these incredibly expensive plants that are only economic if they run 24/7. We need to be going in the opposite direction. We say, don't worry about how much energy it takes. Worry about how cheaply you can build it, because we're going to have 30% of the time, we're going to have free energy in the next 50 years. 2% of the time, energy is going to be free. So stop worrying about energy intensity and start worrying about cheap capital so that we can build these things. You can store water for nothing, right? But so this is the way to be thinking about this.
I kind of had a, sorry. I kind of had a follow-up, I guess, question.
I'm trying to find you here. Yep, go ahead.
So I've been like doing like research and
yes. Hi.
Yes. Hi. I guess to start off, thank you for the talk. It was very interesting, especially the transactive like energy management. I think that's a very like interesting concept that I've never like thought of or even heard of. My question is kind of like a follow-up. So I've been doing research on hydrogen, and my research has kind of jumped into looking at LOHCs or liquid organic hydrogen carriers. I don't know if you've heard or seen of them before, but I was just wondering if you, I guess, kind of piggybacking off of your point.
So is that what we would call ammonia?
Ammonia
is ammonia.
Ammonia is one of them. Methyl cyclohexane, dibenzyltoluene,
okay.
All the fun stuff. So my I guess research currently revolves around thinking about whether or not these LOHCs are viable for like hydrogen storage or even hydrogen transportation, because these liquids are very similar to like water. So you can put them in a pipeline. Like you said, you don't have to worry about like the small molecules.
There's already an infrastructure for ammonia. Ammonia is one of the most manufactured and transported chemicals in the world because every farmer uses it. So yep,
exactly. So I guess my question kind of goes back to like, do you find it, I guess, feasible, or even does it make sense to pursue this field in the sense of continuing to utilize hydrogen as a storage chemical? I know you said that like batteries are very expensive, and I'm assuming these systems are very expensive too because they require high expensive catalytic elements and materials. But do you think this would be a good way to approach this like energy transition on like a larger scale?
I'm probably engaging in anti-hype. So that's so I'm not saying we shouldn't be working on batteries and storage technologies, not by a long shot. We definitely should, right? I just think that they have been overhyped as a solution to the problem. They are not going to be the solution to the problem for a long time. And as I think I said at the beginning, I think this transactive energy management stuff is the low-hanging fruit in this area. This is the stuff that is cheap and getting cheaper. There's a bunch of, so it's just, this is the place to go to like get ourselves to the point where it's actually worth it to have an expensive battery, because we need it in, but we're not going to solve the grid, the bulk storage problem, or not. I mean, when you look at those gas tanks all over the place, you realize, wow, you can store a lot of energy with chemicals. Right? Chemical energy is a really, really good store of energy. So if we can figure out how to do it with biofuels and hydrogen, hydrogen fuels, then I think that's great. And I think that has more promise. And the problem, of course, is that turning that stuff back to electricity is not super efficient. You're back to thermal engines. So you've got a huge penalty there when you start burning your ammonia to generate electricity. Whoops, there goes 60% of the BTUs. But if it's cheap enough, it doesn't matter. So
awesome, thank you.
Great. Thank you so much, Professor Baker, again, for the very informative presentation today. We're at time, so if anybody needs to head out, thank you so much for coming, and definitely stay in touch with the link just sent in the chat. But Professor Baker, if you're available for another 1 or 2 minutes, we can definitely take some more questions.